Hello everyone, welcome back to the channel. In this video lecture, we shall solve this problem longest increasing subsequence. In this problem, we're given an array nums, an integer array, and we have to return the length of the longest strictly increasing subsequence. So what is a strictly increasing subsequence? It is a subsequence in the given array where each element is strictly greater than the previous element. For example, let's see the constraints of the problem. The length of the array that we have can go up to 2500, the length, while the element in the array may go up to 10,000. Okay, so let's better understand the problem using an exemplar test case. Here you can see we have a nums array. In this array, we can find strictly increasing subsequences like this. Although there are more than 2 subsequences, we can see there are, for any array of length n, we have 2 raised to the power n subsequences minus 1 if we do not consider empty subsequence, but we will only consider those subsequences which are greatest in size. So in this array, these are the subsequences which are largest in size. Okay, there can be a sequence like 2, 5, 7, 101, 2, 5, 7, 1, 8. So there are 4 longest strictly increasing subsequences. Okay, so these are the 4 longest strictly increasing subsequences of this nums array that we have. And hence the answer for this problem is 4, because that's the length of the longest strictly increasing subsequence. So now let's see how we can solve this problem. So you can see that to generate a strictly increasing subsequence, all we have to do, we must know that let's say we are constructing a subsequence where we have some element, let's say EL, already present at ith index of the subsequence. So we have some subsequence which is here, and this is the ith element in that subsequence. Now I want to insert the next element in this subsequence. Okay, then the element which I will insert after EL, that element must be strictly greater than this element. Okay, so while constructing the longest increasing subsequence, we have to keep track of the previous element that we have in the current subsequence. Okay, so let's see how we can do this. We start from the first element, we push it in a array, and we say okay, now the subsequence, initially the subsequence is empty, so we are trying to construct a subsequence. Initially we have empty subsequence, then I push 2 in my subsequence, now I have 2 in my subsequence. The another case is I do not take this element in my subsequence. I say okay, maybe the final sequence does not start from 2, it may start from 5. Okay, then I do not take this element in my subsequence and I move to the next element. Now again I have 2 cases. First we have to check if 5 can be inserted in this subsequence or not, and the answer is yes, 5 can be inserted, because 2, which is the previous element, is strictly less than 5. Hence one of the cases can be this, push 5 in this already constructed subsequence, and another case is we skip 5, maybe in the final subsequence we do not have 5, hence we just keep 2 as it is. While here maybe our subsequence may start from element 5, so one of the cases is take 5 as the first element, and we do not have to check 5 with any element because there is no previous element here. 5 is the first element. And another case is we do not take any element and we have empty subsequence. Similarly, that's where we keep repeating this step, namely checking whether the current element can be inserted in the subsequences that we have constructed till now. If it can be, then take 2 cases. One of the cases is construct the final subsequence by inserting that element, and another case is construct the final subsequence by skipping that element. okay, and check which choice gives me the largest length. So I am making two choices here. Although here I had only one choice, while here I have two choices, and all I have to do, I have to check whether this subsequence or the subsequence returned by this, which one of them has largest length. So that's the idea. Okay, let's think of it in a more programming way. So imagine a function length of lis. Okay, so this function returns me the longest increasing subsequence in this array, where prev represents the previous element in the given sequence. So starting from index I and ending at last index of this array here. I is maybe somewhere here, I may be 0 here. So initially this function, let's call it ls, it is called at first index, that is 0, and previous element is taken to be -1. Previous element is taken to be -1 because the array nums contains only non-negative integers. Non-negative means 0 and positive numbers. Hence any element of this array must be greater than -1. Okay, that's why previous element is taken -1 while we are starting. So now I'm standing at this index number 0, and I'm calling this function here. This function, now we can see that the subsequence that we have here is empty. We do not have any subsequence yet. Now we check whether 2 can be inserted here. Yes, 2 can be inserted in the subsequence because the previous element is -1 and 2 is greater than -1. Hence one of the cases is that, okay, take 2 here and move to the next element, that is element number, and the subsequence that we have here contains the other choices. Do not take 2, just move to the next element, because maybe in the final subsequence I do not have 2. It may be the case that the final subsequence starts from 5. So that's why I skip this element and move to index number 1. Previous element here is 2, while the previous element here is still -1 because we haven't inserted a single element in our subsequence yet. Now here we again have two choices. We are standing at this index and we check whether the element at this index, that is 5, is greater than the element that is already present in the subsequence, and the answer is yes, it is greater than 2. So we have two choices. Either we insert this into our final subsequence, that maybe 5 is the second element in the final subsequence. In that case, the subsequence becomes 2, 5. We move to index number 3, or element number 3, index number 2, and the previous element becomes 5 because that's the last element which we inserted in the subsequence. Another case can be we do not take this element in our final subsequence because maybe the final subsequence do not contain this element. So we just move to next index while skipping the current element and keeping the subsequence as it is. Okay, in this way, finally we would have 2 raised to the power n-1 n subsequences prepared. So we would have some subsequences right here, subsequence here, and so on. All we have to do is to return the max of these subsequences, max length of these subsequences. So this function basically returns me the length variable, that is an integer which I have to return to the calling function. So each function call makes at max 2 recursive function calls. The return type is an integer which is the maximum of the lengths returned by these functions. So let's say this function, imagine how the body of this function will look like. You can see that we are standing at some ith element. All we have to do, we have to check if this element is greater than the previous which we are passing here. If it is, then we make two function calls, one by taking in the element and updating our previous variable, and another by not taking in the current integer and keeping the previous as it is. This is the case when ith element is greater than the previous. Otherwise, we just have to make one call, that is skip the ith element and move to the next integer. Okay, so this is how the body of this function will look like. We would have two cases, either take the ith variable or do not take the ith variable, ith integer in the nums array. If we do not take it, we just move to the next element and check for the length of longest increasing subsequence in the array starting from I plus 1 up until n minus 1. Otherwise, we have two options. If the current integer is greater than the previous element that we have in the subsequence, then we take two elements, then we make the function call by taking in the current element as the previous element. So here I am passing nums I, so this is nums I basically, which I am passing here. I'm updating my previous variable. I'm saying okay, the subsequences has previous as the last element, and now I'm standing at ith element. Take this ith element, and now the previous becomes nums I. Length has increased by 1. So this is how the function is working, and we return max of the lengths which we obtain by not taking in the ith integer and by taking in the ith integer. So here we return that. Let's see the time complexity for this implementation. But before that, let's discuss the base case here. What would be the base case? The base case would be when we cross the last index of the array. So when we reach n, that is the size of the array, then that is the base case because we do not have any element to compare with. Hence we return 0. Let's see the time complexity for this implementation. So here we are taking elements, so the length will increment by 1. We are taking in an element, the length will increment by. Now we can see that there are at max two function calls at each. So you can see this function may call at max two functions recursively. Hence the branching factor is 2, while the height of this tree goes up to the number of elements that we have inside this array, that is n. Hence the time complexity is 2 raised to the power n. So it is exponential time complexity. Even for an array of length 100, this would give me 2 raised to the power 100 time complexity. These operations are way too many to be executed within the time limit of 1 second. Hence we have to improve upon the solution that we have here. And there are the next step for a recursive code. So we want to improve upon our recursive solution. We can think of memoizing it, but we must have two properties that our code must satisfy so that we can memoize it. We can see the first property is the optimal substructure property. Okay, that means the solution to a larger problem depends upon the solution of smaller problems, and that is the case here. We know if we want to find the longest increasing subsequence for this array, we would like to find the longest increasing subsequence of this array. So if we know that, we can find the longest increasing subsequence of this array as well, that we can see here. So the solution to a larger problem is being builded from the solutions of smaller problems. Hence it satisfies the optimal substructure property. The second property is overlapping subproblems, that we have the subproblems are repeated. So we can see here ls, this function is called here, it is called here again. Okay, this 3.5 is called here, it is called here again. So we have repeating problems. The problems are repeating, the subproblems are repeating. Okay, hence we can memoize it. Memoization means once the results for a particular function call is evaluated, we store it somewhere so that here we require the result again. All we have to do is to return the results right from here so that these unnecessary computations are not performed. So this is the idea of memoization. Let's see how we can memoize this code. So you can see that for memoizing the given code, you can observe that at each level, at each function call, there are two variables which are changing. The first one is the index variable, the another is the previous variable. Hence, our dynamic programming table or our memoization table would have two dimensions. Okay, so let's see the memoized code. So this is the memoization which we performed over this recursive code. So this dimension represents the indices n, so we have n indices, while this dimension represents the previous element that we have. So this is the memoized code. All we did is, this is the case of memoization, so we initialize this array with -1. This is because we want to check whether the result for a particular index and previous pair is calculated or not. If it is calculated, if it is already calculated, that means, let's say the computation for index 2 and where the previous element was 5 has been performed here, then for that particular dimensional variables 2 and 5, we assign the result of this function call, and here we require the result again. All we have to do is to return the result which we stored here. So that's what this case is checking, and here we take two variables, take, do not take. This represents that we are not taking the ith variable into our subsequence, and this represents that we are taking that variable. And if we do not take it, we just jump to the next integer while keeping the previous as it is. Okay, otherwise this is the case when previous is equals to -1. This is the case when we are starting. So when we are starting, then we pick the element, we pick the first element, and this is the case where where we are standing at ith integer, and that integer is greater than the previous integer that we have. So this is basically the index of the previous integer in the subsequence. So in this case we are taking the ith integer, hence the last integer that we have in the subsequence becomes the ith integer that we have, and hence we pass the index of that variable, index of that integer, and we call the function for the next for the subsequence starting from i+1, and we increment the answer by 1 because the subsequence has been the length of the subsequence has been increased by 1 since we have taken the ith element into our subsequence. And here we take max of these two options, so whatever the option returns me the largest value will be assigned for that particular integer and previous value. Here we are assigning that. How it has improved the time complexity, let's see that. You can see that computing the results for unique I and j pairs. So what are I and j? These are the indices of this. I represents the index of the current element, while j represents the index of the previous element that we have, or the last element that we have inserted in our longest increasing subsequence. So we have to consider the unique I and j pairs, because once the function call for a particular pair has been performed, the computations performed, they will not be performed again. So how many unique pairs of these indices are there? If we see that the index I goes from 1 to n and the index j goes from 1 to n, then the time complexity would be n into n, or the number of pairs, unique pairs that we have, and we are taking in the ordered pairs. So 1 2 is not equal to 2 1. In that case we have n cross n pairs, and hence the time complexity is big of n square, while the space complexity is also big of n square, since we are using a dynamic programming table of 2 dimensions which have of size of dimensions n cross n. So this is the space complexity. Okay, so we have improved our time complexity of the recursive code, but at the cost of auxiliary space which this matrix is consuming. What is the most optimal approach to solve this problem? Although it will work for the constraints which we are given here, that is 2500 into 2500 represents 625, which when divided by the number of iterations that a computer performs, it will give me and this is within the time limit of the judge, that is 1 second, and hence we can use this code to solve this problem. Okay, but maybe the constraints are not that small. In case n goes beyond, let's say 10 raised to the power 4, so if the n becomes 10 raised to the power 5, so in case n goes 10 raised to the power 5, then this code will obviously not work for these constraints. Hence we have to improve upon our logic to solve the problem for these constraints. This is the greedy approach with binary search. Imagine we are starting with a subsequence, so we're trying to build subsequences, okay, in a greedy way. So this is the parent array, the nums array, and this is the initial subsequence that we have. Initially it is empty, and we insert the first value in our subsequence. So now the subsequence that we have contains one value. Okay, now we move to the next number, that is 6, and we insert 6 into our subsequence. Now we have subsequence 2, 6. The length of the subsequence is 2, and then we move to the third integer, that is 8, and now the subsequence becomes 2, 6, 8. This is because we see that 6 was greater than 2, hence we inserted 6. 8 is greater than 6, hence we inserted 8. So we are building strictly increasing subsequence, and now we are at this integer. We see that 3 is not greater than 8, 3 is not greater than 6, but 3 is greater than 2. So we are taking another subsequence, because what we are saying here, okay, maybe we cannot insert 3 here, but there can be a subsequence where the second element of that subsequence is 3, and maybe this subsequence is greater than this, will become greater than this subsequence. So that's why we are exploring the another case. So all we did, okay, 3 was not greater than 8, but we found an element which was just smaller than 3, and that was 2, and we just took the subsequence up until that element and we created another subsequence, because we are exploiting another case and saying, okay, maybe this subsequence will become larger than this subsequence. Now we move to next element, that is 4. Here you can see that we cannot insert 4 in this subsequence because 4 is less than 8, while we can insert 4 in this subsequence because 4 is greater than 3. Hence this subsequence becomes 2, 3, 4. Then we move to 5. We cannot insert 5 here again, but we can insert 5 in second subsequence because 5 is greater than 4. So the subsequences becomes 2, 6, 8 and 2, 3, 4, 5. That's why we took. So you can observe now here. You can observe why we chose to take another subsequence here, because this subsequence exceeds the size of this subsequence here at this point. Now let's see the next element. The next element is 1, and we can see we cannot insert 1 here because 8 is greater than 1. We cannot insert 1 here because 5 is greater than 1. Hence we take another subsequence that contains only this element. Now we have 3 subsequences generated, and we can see the largest subsequence out of these 3 subsequences is this, and it has a size of 4, and we return 4, which is the answer for this given input data. So here what we are doing, we are greedily generating the subsequences. We are basically starting with one subsequence, and so we're starting with one subsequence, and as we move along we're building more subsequences and exploiting all the cases. So these are all the possible subsequences that we can generate. But in this case, what is the problem with this approach? You can see that while we are iterating over this array, it is very hard to generate these subsequences. So that's why the space complexity for this solution is way too high. We have to improve upon our space complexity, although the time complexity has improved a lot. Let's see how why we have written binary search here. So you may have some idea that to insert some element, let's say this, we have to check the element in the already formed subsequence, which is just smaller than this element, and that is the lower bound scenario. So we have to check the lower bound of 8. Let's see how we can, okay, so let's see how we can construct the solution. So this is the nums array, initial array, and this is the initial subsequence which is empty. So this so in the first step we are standing at this integer and we insert this integer into our subsequence. Then we move to the next element, that is 6, and we insert 6 into our subsequence because 6 is greater than 2. Then we move to 8 and we insert 8 here because 8 is greater than 6. Then we move to 3 and we see that okay, 3 is not greater than 8, 3 is less than 8, so we cannot insert 3 here. In the previous case we generated another sequence which would start with 2 and end with 3 here. So another subsequence that we would have generated with previous case is this. But since we are improving upon space complexity, all we have to do is just overwrite the subsequence that we have here. So what we do, okay, we find the first element which is strictly smaller than the element which we want to insert. Okay, so we want to find the first element in the already constructed subsequence which is just greater than the element we want to insert. That's what we want to do, and for that we use binary search or lower bound. Okay, so we perform lower bound over this subsequence and we see that okay, 6 is the element which is just greater than 3, and we overwrite this 6 with the element we want to insert. So we overwrite 6 with 3, so the subsequence becomes 2, 3, 8. Then we move to next integer, that is 4, and we see okay, 4 is again less than 8, so we find in this subsequence the first integer which is just greater than 4, and that integer is 8, so we insert 4 in this place. Then we move to the next integer which is 5, and we see okay, 5 is greater than 4, hence we can insert 5 here, so we insert 5 in this subsequence. Then we move to 1 and we see okay, 1 is not greater than 5, the last element of the subsequence that we have, hence we perform lower bound over this subsequence, that is the first, that is to find the index of the first element which is just greater than 1, and that element is the first element, and hence we overwrite that element here. Okay, so with this what we are doing, we are simply overwriting the already constructed subsequence, and by this finally we get our answer subsequence which has a length of 4. Okay, so that's the idea. We are performing binary search to find the required position where we want to insert our current integer. So let's see how we can implement this solution in code and analyze the time and space complexity for this solution. So here is the function that we implemented. We initialize a subsequence of empty array which stores the final subsequence, and n is the length of the nums array that we are passing. So we iterate over the subsequence, so we iterate over the array and we check if the subsequence is empty. This is the first case. Then we insert the element and we check if the last element that we have in the subsequence is less than the element that we want to insert. If that is the case, then we insert that element because that's what the question demands. We want to find the subsequence which is strictly increasing. Otherwise we find the first index where the element in the subsequence is strictly greater than the nums I, or the element that we want to insert, because here in this case the nums I is less than the last element of the subsequence. After that, at that index we overwrite the integer with the current integer, okay, the current integer on which we are standing. And finally we have our subsequence constructed and we return the size of that subsequence. And that's all we are doing in this code. And let's see the time and space complexity for this implementation. So you can see that we are using an extra array of which has a size of n in the worst case. In case the entire array nums is strictly increasing, the sub will store the entire array itself. So the space complexity is big of n, and the time complexity is, so we are iterating over the array, it is contributing a linear time complexity, while for each element we are performing a binary search. Binary search takes log of n time, so we are performing binary search over the subsequence array, and subsequence may have a length of n in the worst case, so log of n here, and that will give me a time complexity of big of n log n. Now this is a considerable improvement upon the space complexity as well as on the time complexity from the previous code, where the time and space complexity was quadratic. This will work fine for the constraints where n goes up to 10 raised to the power 5, and we are using binary search here. Let's see how lower bound is implemented, how to find the first element which is just greater than the element that we are passing. Okay, so this is the C++ implementation for the length of longest increasing subsequence. So here we are declaring the vector, the subsequence, which will store the subsequence, and we are iterating over all the indices, and these are the conditions where the element that we are standing is strictly greater than the last element. So we push it, otherwise we perform the lower bound and update the element at the index that we get from this lower bound, and finally we return the size of that subsequence. Okay, so this is the implementation in Java language, and this is the implementation in Python. Okay, so I have attached the solutions in the description, so make sure to check it out and stay tuned for more such videos. Thank you so much.